You haven't seen Chris Hadfield? He made the music video in space. He covered David Bowie's A Space Oddity in space. It's up to about 85 million views, I think, on YouTube. Meanwhile, let's begin our next unit. One of the tricky parts here is the words in physics have different meaning from the words in English. We're going to talk about work. When I say I'm doing work in English, you typically mean I'm getting tired. Work is not tiredness. There is a physics equivalent of tiredness. It's power, and we'll talk about that in the next lesson. But work is not tiredness. When you do work on an object, you change the amount of energy that it has. So in physics, work has a specific meaning. In physics, work is not doing something that makes you tired. Logan, instead, work is done on an object. You do work on something. And if you've done work on something, you're going to write this down, you've changed its energy state. You back with us now, Jackson? Because I don't know where you were, but it wasn't here. For you to do work on an object, there are two conditions, two things must happen. First, a force must act on the object. Mr. Dueck, does that mean F equals ma and free body diagrams are back? Yeah, which is one of the reasons I saved this unit for last, because it's going to be some good review. So you have to have an unbalanced force acting on the object. And the work must move through a distance in the direction of the force. Work is a scalar. It has no direction. And it's calculated by work equals force times distance. Find that equation on your formula sheet, please. It's about 2/3 of the way down, and that's the work and energy section. I think just beneath the forces section, you'll see W equals FD. See it? All those equations right next to it and one line below it are what we're going to be doing. And I think momentum, by the way, is just below that section. I need to flip-flop them next year because I changed the order that I teach things. I need to put momentum above work and energy. Although you can find stuff on your sheet. What would the units be? Well, what are the units for force? Newton times. What are the units for distance? Meters. Work is technically measured in a Newton meter, but it's such an important concept, we give this unit a special name. We call it a joule. Symbol, capital J. Named after a scientist whose last name was Joule. Now, this equation here, work equals force times distance, we said there must be an unbalanced force. In fact, if you want to, you could put a little tiny net there if you wanted to. There has to be an unbalanced force. If the forces are balanced, no work is being done. And the object must move through a distance in the same direction as the force. There's a third condition. The force has to be constant. It can't be a changing force. I will show you a workaround that we can use using Physics 11 skills for a changing force, but they have to give us a graph. How much work does it take to lift a 12-kilogram mass from the ground to a height of 9.5 meters? I'd like you all to underline the word lift, please. One of the most common examples of work is lifting an object. When you lift an object up, you're storing energy in that object. How do I know? Because when you let it go, it will move on its own to get back down to the earth. An object can't move on its own unless it's got some stored energy. So when you lift an object up, you're storing energy in the object. How much? Well, Rowan, what's our new equation for work? Work equals? Yep. When you're lifting an object, that's a vertical distance. And in fact, what we often do, can you do me a favor, leave a space? We replace the D with an H for height. When you lift an object, what force are you working against? Okay, don't write, well, we're going to do a free body diagram. I was going to say don't write this down. I'd just like you to think, here's Rowan lifting. What are the forces acting on? To get the obvious one. If you're lifting at a constant speed, I'm going to argue that the force of the lift, if you're lifting at a constant speed, is exactly the same size as gravity. So don't write this next bit down. Technically, I would write force, don't write this down, of lift, but in the same way that for the normal force, I often said, oh, but look, I know another force the same size as the normal force. Oh, but look, I know another force the same size as the force of lift. If you're lifting at a constant speed, what is it? More specific, those two letters. The force, the work done when you're lifting an object is mgh. Now, you'll see on your formula sheet an mgh, but you'll see it's not called work. It's called PE, I think. Is it not? And that's because we're going to go one step further in a couple lessons. We're going to say not only did you do work, you stored potential energy in the object. That's why when you let it go, it will fall. So PE is mgh. That's also the same as the work done in lifting an object. Let's crunch the numbers. Rowan, what's the mass? Yep. What's G? You all know this number. Do you remember? 9.8, and we're scalarville, so we're not going to call it negative 9.8, 9.8. What's the height? Yep. 12 kilograms, that's about that lead weight in front of Adam there, roughly. 9.5 meters, that would be like carrying it up about 3 flights of stairs. You know what? That'd be about the amount of work carrying up those 3 flights of stairs behind me here, this double big flight of stairs to the top floor there. About, roughly. What do you get? 1,117.2. I'll go 1,120. I'll go to 3 sig figs. Jules? Is that a lot of work? Would you be huffing and puffing if you carried that weight up the stairs? You know what? It would depend on how fast you did it. And that's why I'm saying work is not tiredness. But you could do it. All of you can output fairly easily without getting tired too much, fairly consistently around 1,000 joules. And you don't notice it much. Cole pushes against a brick wall as hard as he can for 12 seconds, and amazingly, the wall does not move. How much work has he done? What's our equation for work? Force times distance. Why is the answer here 0? Wall didn't move. So Antonio, could you do me a favor? Could you stand up? Could you go to that section of wall underneath the quantum physics poster there and push? Now, this is why, keep pushing. Push hard. This is why I want you to realize work, keep going. I want you to keep going while I'm talking. Work is not the same as tiredness. If I made him do this for half an hour and push as hard as he could for half an hour, would he get tired? Yes. Has he done work? Not in physics. Okay? Thanks, Antonio. You can sit. If it does not move, you have not done work on it. Specifically also, if it doesn't move in the same direction as the force, you have not done work on it. Example 3. Suppose you're pushing an object across the floor and it requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? Well, first of all, work equals force times distance. I'm imagining that we're sliding some kind of a box and the force applied is 22.5 newtons and we're moving it 13.6 meters. If you want to do a little sketch like that, you can. You don't have to. Here's my point. Is there an unbalanced force? Yes. Is there a distance? Have we done work? Yes. So we're just going to go straight and multiply. 22.5 times 13.6, which is what? 306 units for work, joules. A couple of lessons from now, Ben, you'll learn that energy is defined as the ability to do work, and so energy is also measured in joules. You may have learned a bit of that last year. If your Science 10 teacher did the new Science 10 curriculum where they looked at potential and kinetic energy, you may have learned what a joule is. It was the transition year, and so some of your Science 10 teachers may have done the old Science 10 physics curriculum where you look at distance and velocity and time. I don't know. Gonna make it, Kenley? You sure now? Well, sit up. One of the reasons work is so nice is that it's a scalar. Dylan pedals his bike up a 19-meter high hill that is 91.4 meters long. The combined mass of the bike and the rider is 65 kilograms. The bike requires a steady force to continue up the hill. Thought problem. Suppose Dylan had used a rope to lift himself and the bike hand over hand up the backside of the hill. How much work would that require? Well, this is the work done if you're lifting an object. From the previous page, what was the equation that force times distance morphed into for lifting? Do you remember? Yep. So it's going to be the bike and rider are 65 kilograms. G, Rowan pointed out, is 9.8. What's H in this question? How much work would he do if he just climbed the back of the hill? Give it to me exactly. What was it? 12,103. Anybody else? No? Yeah? Yeah? Units, Adam? Okay. What if instead of climbing up the back of the hill, he bikes up at a 12-degree angle for 91.4 meters? How much work will he do? This is the beauty of work and energy. It's a scalar. When you're biking up a hill, which force are you doing work against? Be obvious. Why is it hard to bike uphill as opposed to biking on level ground? You're doing work against the force of gravity. So if he's going the long way, it's going to be the force of gravity, but the distance has to be in the same direction as gravity. The distance has to be in the same direction as gravity. And so you get the same equation. It's going to take him 12,103 joules of energy to bike up this hill. Why? Because the force at play here, Mackenzie, is gravity. And then the direction is the height of the hill is in the same direction as gravity. What the hill does is it allows him to spread the work out over a longer time. But it doesn't change how much work he had to do. If this was an even shallower hill, but he's still reaching a final height of 19 meters, Kenley, this distance would be longer, but this number here won't change. What I tell people is when we're talking about work and energy, all it cares about is where you started and where you ended. It doesn't care about the path in between, which means it doesn't care if the hill does this along the way, which means it's our best tool for analyzing roller coasters. Okay? We'll learn how to do that shortly. Now, if that's how much work I have to do, how much force will I have to pedal with? Work equals force times distance, but this time I want to find the force of pedaling. I'll call that FP. Rowan just jumped ahead. Rowan, how did you get the F by itself? Divide what? Let's use nouns, please. What? Yeah. So I can now that I know how much work it's going to take no matter what just to do it vertically, I can say, okay, the force of pedaling is going to be the work divided by the distance. It's going to be 12,103 divided by which distance? If he's going up the hill in this direction, if he's exerting a force in this direction, which distance do I have to use? 91.3. 4. What'd you get? Sorry? 132. Anybody else? 133. Anybody else? 133.4. So 132. Rounded off properly. By the way, if he was lifting himself straight up, hand over hand, he would have to use mg. He would have to use 637 newtons. A ramp, like a hill, it's a force multiplier. You still have to do the same amount of work, but you don't have to push as hard. The ramp is one of the biggest inventions of humanity. The Egyptians, as far as we can tell, didn't invent the wheel, but they invented the ramp, and they were able to build the pyramids just with the ramp, because you make a nice shallow ramp, you have to push it a long distance, but you won't have to push very hard. It's not the same as lifting it. Ramps are force multipliers. Is that all right? Work equals what times what? Force times distance, but there's a couple of conditions. The force has to be constant, not changing, and the force and the distance have to be in the same direction. Turn the page. How much work would it take for Dylan to ride to the top of this particular bike hill? Well, what force is he doing work against? Gravity. You know how much work it's going to take? It's going to take mgh. Mr. Dueck, it's the same height as on the previous page. It's 19 meters. So you're saying it's going to be 12,103 joules of energy. Same height. Okay. If you ask me if I can ever use energy to solve a problem, I will try and use energy to solve a problem, because no direction. I don't have to be as careful, especially if I have a curvy, yucky path. Okay. What takes more work, lifting a 25 kilogram mass to a height of 4 meters or lifting a 50 kilogram sack to a height of 2 meters? Same. In fact, because it's lifting, we can calculate it. mgh, it's going to be 25 times 9.8 times 4, which is 100 times 9.8, it's 980 joules. And if I find the other one, it's going to be 50 times 9.8 times 2, 980 joules. I calculated that also because this works out to almost exactly 1,000 joules. If you're just trying to figure out what's really big and what's really small, it takes 1,000 joules of work to lift 25 kilograms. It's about 65 pounds. A small kid, like a 7 or 8 year old, to a height of 4 meters, if you were giving a kid a piggyback up a single flight of stairs. That's about the amount of work. Or most of you weigh around 50 or so kilograms, plus or minus some. It would be like giving a piggyback to a teenager up half a flight of stairs. That's about 1,000 joules, roughly. Obviously, there's a big difference depending on how much mass the kid or the person has. Next page. What if the force is not constant but changing instead? You're going to learn 3 definitions of work. You've already learned the first one. Work equals what times what? And what you're going to do whenever a question says, how much work? You're going to first of all say, can I solve this using force times distance? Nope. Then you'll move on to method 2. Can I solve it with method 2? Nope. And then you'll move on to method 3. Method 3 is the most universal, but it's also the most cumbersome. I'll do a whole lesson on it. It sucks, but it works. No pun intended. Here's method 2. Work is also the area underneath a force versus displacement graph. Sam, can you read example 7 to me? How much what?
Work.
Okay. Now look up. I can't go force times distance because can you see here the force is getting bigger. It's not constant. It starts out 2 newtons and finishes 8 newtons. Start reading again. How much?
How much work was done in moving the object from 2 meters to 5 meters?
Everybody do a little dotted line like that. A little dotted line like that. There's your 2 meters to 5 meters. Everybody do a little dotted line like that. A little dotted line like that. There's your 2 meters to 5 meters. The answer is going to be this area. This shape, don't write this next bit down, where you have 2 parallel sides and 2 sides that aren't parallel, has a special name. It starts with letter T. Anybody know what it's called? TR. TRA. TRAP. Trap. The trapezoid. You've heard the word. I always ask for a candy, and sometimes they teach this in Europe. We'll see. Does anybody know the formula for the area of a trapezoid? There is one. I see you doing that. We'll see if you have. There is one, Mackenzie, but it's redundant. You don't need it. And the reason is every single trapezoid on Earth can be divided into a rectangle and a triangle. And those you do have formulas for. I know you've been taught the area of a rectangle, and I know you've been taught the area of a triangle. And so almost certainly I will give you a lovely trapezoid. And what you'll do is this. Yoink. Draw that line in. Let's call the rectangle area number 1. Let's call the triangle area 2. Do that. The amount of work done is going to be that area. I'm going to find the area of the first shape. It's a rectangle. How do you calculate the area of a rectangle? Loud and proud. Now, if you don't know this, you might want to flip your green sheet over and somewhere in the bottom, right, area rectangle equals length times width or something like that. Antonio, what's the length of this rectangle? Don't say 5. 3. What's the width of this rectangle? Don't say 1. Look at the scale carefully. Yeah, it's going up by 2s, I think. Yes? In your head, Antonio. Thank you. Then I'm going to find the area of the second shape, the triangle. Does anybody remember what the area of a triangle is? I'm going to give you a hint. Here's how I remember it. I actually, instead of memorizing length times width, I often called it base times height because a triangle is half of a rectangle. Rectangle. Any triangle is half of a rectangle. What would half of that be? Base times height divided by the triangle. If you don't know that, you may want to, on the back of your formula sheet, somewhere near the bottom, write down area of triangle. Or you could smoosh it in somewhere near the energy section, whatever. So, what's the base of this triangle? How long? Don't say 5. It's not 4. 3. What's the height of this rectangle? Don't say 8. How high at the top? 8. How high at the bottom? 2. 8 high, 2 high. Hello. 6. Divided by 2. Can we do that in our head? 9. I mean, yeah. We can do that in our head. 9 plus 6. And by the way, On a test or a quiz, even for stuff that I find this simple, I probably would type it into my calculator because I've lost track. This one in particular, the number of times I've gone 3 times 2 is 5 because my brain added them instead of multiplying, and those numbers are associated in my brain. So don't be embarrassed on a quiz or a test to use your calculator. And honestly, if you're not great at your times tables, use your calculator. But I'll nudge you to do stuff in your head. 9 and 6? Yes. Units, it's work. What did we just say the units for work were? Joules. Okay. 15 joules. We added the 6 plus 9 to get the 15. We did it in our head. And then it's work, so the units are joules. It's a J in theory, but my writing is messy. I'll never make fun of someone from... I shouldn't have made fun of you because my writing is bad. Like I said at the beginning of the year, I would never make fun if you asked me to translate. So now we have 2 definitions of work. The first is the equation work equals what times what? Hello, work equals what times what? I'm not going to write the times, I'll just put the letters side by side. This requires a constant force. Or work equals the something under a something. Area under a force versus distance graph. How do I know to use the second one? They gave you a graph. Don't overcomplicate it. If there's a graph in your question, probably it's a changing force. You'll notice if the force is slanty, if the line has a slope. Couple more, we're done. Example 8. Jabber, when you're done yawning, what's example 8 want me to find? Why can't I go force times distance? So every year I see some kid, they say, well, why can't I just go 30 times 10? Force times distance. What did the force start out at? What did it finish at? It's a changing force. Fellas? So it's going to be this area here. You will get 3 shapes. It might be a rectangle, length times width. It might be just a triangle, not a trapezoid, base times height divided by 2. Or it might be a trapezoid, which is a rectangle and a triangle. I have yet to meet a trapezoid that I can't divide into a rectangle and a triangle. So I'm going to find the area of the first shape. What shape is the first shape? A rectangle. What's the area of the rectangle? Length times width or base times height? I don't care which. It's going to be 10 times 20. And I got that right from the graph. But look at your units, by the way. Don't say, well, isn't it 2 squares? Isn't the base 2? Look at the numbers on the graph. I can do that in my head, 200. And then area 2, it's going to be base times height divided by 2. The base is that line right there, which is 10. The height is this line right here, also 10. You figure that out, Adam, just by looking at the axes and doing some subtraction. Over 2. Adam, in your head, 10 times 10? Divided by 2. Adam, in your head, 200 plus 50. How many joules of work? Yeah. Now we're going to kick it up a notch and do some nice review. When you push, for example, the big benches in the gym across the gym floor, you're doing work. You are applying a force over a distance, and the force and the distance are in the same direction. So here is like that, except it's a really heavy box. Cut it out. This box is 124 kilograms. How many pounds is that? Just shy of 300 pounds. So you'd be doing a lot of work. Okay? We're pushing it along the floor that has a coefficient of friction of 0.25. The person applies a force of 525 newtons over a distance of 22 meters. The first question is this. How much work is done by the person pushing? You know what? Is there a coefficient of friction here? Let's do a free body diagram over here. What are the forces acting on this box? Get the obvious one. Courtney, you're on today, yes. Courtney, is it sinking into the ground like quicksand? Is it flying you like Superman? So there's a normal force pushing back up. There is an applied force. They even use the word applied force. This is the person pushing, and it is F applied, and I'll even put the number 525 newtons. Give me 1 second, hang on. Is there friction in this question? How do you know? They gave me that coefficient of friction. I'm not sure if friction is bigger or smaller, but you know what? At least I've got everything covered, I think. All right. All right. Kenley, what does A want me to find? Keep reading. This is important. By the... You know what? I think they want me to find the work done by the applied force. Work is what times what? So I think work done by the applied force is going to be force applied times distance. They are in the same direction. I'm using my imagination, but sliding across the floor would be in that direction. So I can, I think, just plug and chug here. It's going to be 525 times 22, which is what? 11550 joules. Anybody else? Yeah? Okay. That's how much work this person did, but not all of that went into moving the bench. Some of that work went into overcoming friction. That's why B says, how much work is done in overcoming friction? Well, I think that's going to be the work done by friction, which I think, Evan, is going to be the force of friction times distance. Friction is what times what? Mu times the normal force times distance. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. Mu times m times g times d. The work done in overcoming friction is going to be 0.25, 124, 9.8, 22. Point 0.25, 124, 9.8, 22. And I get 6,683.6. Why is this technically wrong? I always pause to see if somebody can have that moment here. This is technically wrong. How come? Ben, which way is this box moving in my diagram? To the, give me a word that starts with the letter R. Which way is friction acting? And I said that the force and the distance had to be in the same what? Okay. Or they can be in opposite directions, but how would I show an opposite direction? And what we're really saying is that's energy that was lost to friction. Whatever is left over went into causing this box to speed up. The net work done, it's going to be 1,550, take away 6,000. 683.6. You can add them together if you called the friction negative, or if you didn't call the friction negative, it's going to be the bigger one minus the smaller one. No matter what, you're losing that energy to heat. You actually are heating up the floor. You may have even noticed if you push down with your hand on the desk and pull quickly towards you, you can generate enough heat on your lab tables to actually burn your skin. There's a lot of energy being lost to friction. 11550 minus answer button. 4,866.4. And believe it or not, in a few days, using that number, we'll be able to figure out how fast the bench is moving or the box is moving. We can figure out a speed. Or if it's a roller coaster, how fast it's traveling at the bottom of the first hill, because that's really what we want to know. Okay. This last one here, example 9, it's got some teeth to it. But for now, what's your homework? Definitely number 1 is good. You're going to notice fairly often I'm giving you answers in scientific notation. It's because we're getting towards the end of the year and it's a good chance to review some scientific notation with you. Also, you'll find often your answers are in the tens or hundreds of thousands of joules if it's a big amount of work. 2 is good. 3 is good. You can skip number 4. Ha 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 ha, Mr. Dueck. 5 is good. 6 is good. So far I like 7. I may assign most of these. 8 is good. 9 is good. Yep, I'm assigning I think all of these. And 10. I'm also going to come around and let you know how you did on your test. And I'll also let you know what stuff you're missing. Okay?